Our next speaker is Andrew Miller from Utrecht University, and he will tell us about continuous gravitational probes of dark matter. Please.
Yes. Well, thank you very much for having me here. And yeah, I'm going to talk about a different way to probe dark matter with gravitational waves. So not what you're maybe used to, which is through the merger of compact binaries like black holes, but through the emission of long-lived and quasi-monochromatic gravitational waves, which are called continuous waves. So just to give you some background and some motivation as to what continuous waves are, they're almost sinusoidal, and they're persistent signals, and they're typically subject to a Doppler modulation. So there could be an isolated black hole that has a boson cloud around it, like Masha had talked about earlier today, and this system would emit a quasi-monochromatic gravitational wave from some place in the sky, and it would do so almost forever if it's a scalar cloud. And unlike the signals that come from compact binaries, these last for a long time, and so the longer that we can observe for, the more sensitive we are to these kinds of signals. And this would also be a completely new type of gravitational wave signal, whether it's detected from an isolated neutron star, which is the canonical continuous wave, and also could be linked to dark matter if it's from a boson cloud, or it's from a type of dark matter that I will talk about in this presentation. And the other nice thing about continuous waves is that they're not one-offs like binaries. You can keep observing them for a very long time, so you can keep refining parameters and getting more and more confident in your detection. And there are so many sources of continuous waves. I'll focus on the dark matter ones. And there are so many methods that have been designed to search for continuous waves that also have applications beyond just continuous waves, but also in future detectors for any kind of long-lived signal. So I'll just somehow talk about these three things in the time that I have. The first will be the direct detection of ultralight dark matter particles with the interferometers. These are actually not gravitational waves. This is purely using the interferometers as a direct dark matter detection experiment. And the second and third things are gravitational waves that could come from in-spiraling primordial black holes in a binary system, and could come from boson clouds around spinning black holes. If I have time, I'll go into the third one. So for the direct detection of dark matter, so the idea behind this type of search, the physics behind this, is that depending on what type of dark matter, ultralight dark matter that you believe exists, it will couple in a different way to different particles in the interferometer. And so in the example that I will discuss in this talk, for vector bosons, dark photons, these would couple to baryons in the end mirror, or actually all of the mirrors in LIGO and Virgo. And so because this is a vector signal, there's some spatial component. So there's some spatial component to this signal. So each of the mirrors that are embedded in this dark matter field existing on Earth would essentially move in a slightly different way because of the dark photon, because they exist in this dark photon field. And so as Masha said this morning, this dark photon has like a dark electric field, a dark magnetic field, and this is what's actually moving the mirrors. And so because the mirrors move in a slightly different way over time, this gives rise to a quasi-sinusoidal signal that appears in the detector because there's a differential strain on the interferometer. And so the way we model this is that there's a superposition of plane waves whose velocities follow a Maxwell-Boltzmann distribution, which means that there's a very small frequency spread on the order of 10 to the minus 6. So this is 2 orders of magnitude smaller than the frequency spread you get from the Doppler, just to put this in context. So this really is a purely monochromatic signal with some small frequency modulation. And so you can see here that this is a picture of the 2 LIGO observatories, and this kind of dark matter signal would be correlated in each of the observatories because the coherence length of the signal is much, much larger than the separation between the Earth-based observatories. So I'll just dive into the results. And so we did a search for this dark photon, dark matter in the most recent observing run of advanced LIGO, Virgo, and Kagra. And what you see here on the y-axis is the upper limits that come from the search on the coupling strength of dark matter, of dark photons to baryons in the LIGO Virgo mirrors as a function of the frequency of the dark matter signal or the mass of the dark matter, whichever you prefer to read in. And in the color, the red and the blue, you see the limits that have come from our searches compared to the green and purple curves, which are the limits that come from other dark matter experiments that were actually designed to search for dark matter, direct detection of dark matter. And so you can see that above 100 hertz or so, that the limits that we get are orders of magnitude better than the existing experiments, which is pretty remarkable given that we're essentially applying the same techniques we use to look for other types of continuous wave sources to just this new problem of direct detection of dark matter. Also, it's not just limited to ground-based detectors, so if we think more to the future now, this type of dark matter will also couple to the mirrors in LISA, and we can even get a sense of what the challenges will be in the type of analysis that we will do in LISA by looking at LISA Pathfinder data and doing a similar kind of dark matter search for particles that could have coupled to LISA Pathfinder mission when it flew, I guess, in 2016, 2017. And here you see the same plot, coupling strength as a function of dark photon mass, but you see that the mass range is shifted down by a few orders of magnitude. This is because the LISA frequency range, sensitivity range is a few orders of magnitude lower than LIGO Virgo and ground-based detectors. And so there's 3 curves on this plot. I will just say that these are not constraining limits right now, but the kinds of studies that we have to do and the things we have to deal with in terms of the data analysis, so with gaps and non-stationary noise and very low sampling rate at low frequencies, these are problems that we will have in LISA, and we have at least developed ways of dealing with those problems in this study. And so the future is bright for this type of dark matter and future detectors as well. So now I'll talk about primordial black holes. So these gravitational waves will come from very light primordial black holes that inspiral towards each other over time. And so just to give you some motivation as to why we should care about this, so the previous speaker, one of the previous speakers discussed about primordial black holes and why these are important. So it turns out that there's a lot of gravitational wave efforts to detect primordial black holes, but they mostly focus on the so-called subsolar mass regime, which is on the order of 0.1 solar masses, and they don't really go below that. And the reason for this is because if we want to use the conventional, the ideal signal processing technique, match filtering, when you look at masses of primordial black holes lower than this, the computational cost becomes way too large because the signal durations become very, very long. So the signal duration is inversely proportional, or directly proportional to, inversely proportional to the mass, and so longer signals are at smaller masses, and so this whole range of primordial black holes masses has not been searched for with gravitational waves. And while there have been studies that have been done for primordial black holes in this mass range, a lot of the constraints that you get in those experiments are model dependent. So they depend on how and when primordial black holes formed, whether they formed in clusters or not. So these constraints can actually be evaded. So gravitational waves can give you a complementary probe to primordial black holes in this particular mass regime. And here I just show an example plot of the kinds of constraints that we put with gravitational waves. So on the y-axis is the fraction of dark matter that primordial black holes could compose as a function of the primordial black hole mass. And you can see that the fraction is below 1. This is what we hope. And so the reason that these signals are continuous waves below this mass regime is that because they have very small spin-ups, so they are inspiraling very slowly towards each other, and they will also last for a much longer time compared to what you're used to for black holes that merge. And so with continuous wave search results as they are, the typical ones that are done all sky search for continuous waves from isolated neutron stars, you can basically map these to limits on the distance reached to a binary primordial black hole binary under the conditions that you only allow for linear frequency evolution, and you restrict the spin up, so the rate at which they are inspiraling towards each other, to about 1 microhertz. And so here you can see a plot on the this essentially a quantity that relates to this fraction of dark matter that PBHs could compose as a function of the secondary mass M2. So here we consider an asymmetric mass ratio binary where the primary mass is 2.5 solar masses. So this is really an asteroid mass primordial black hole. The color is the rates. And so this is not actually yet constraining because the fraction is above 1, which it doesn't make sense. But if you look at this region here in 04 and 05 and in the future ground-based detectors will be able to put constraints on this, this region here. And so this also motivates the discussion of maybe we should devise new methods to look for primordial black hole binaries in this planetary mass or asteroid mass regime. And so we have actually been able to do this, and we've shown that this fraction of dark matter that primordial black holes compose can be pretty well constrained to well below 1 in future detectors such as Einstein Telescope or Cosmic Explorer. And so you see here, this is the same kind of plot, the fraction of dark matter as a function of the Chert mass. And you can see that for all these lines correspond to essentially different distances at which you want to quote a constraint. And for the advanced LIGO, which is this orange curve, and you can see that for these higher Chert masses that we are able to say something about, we are actually able to be sensitive to primordial black hole binaries. Now in the minute I have left, I will just basically flash some results about boson clouds around spinning black holes. And so I will skip this because Masha gave a very good introduction to superradiance. And I will just talk about what we can do with continuous waves. So again, we can search for isolated black holes that have formed at some point. We don't know when they formed. It doesn't really matter because the gravitational wave will still be emitting because the cloud takes us such a short amount of time to build up compared to the emission time. And so what you can do is you can do an all-sky search for these spinning up systems, and you can you can essentially eliminate the possibility that there's a particular boson mass and black hole mass at a given distance with a given spin at a given age that would have produced a gravitational wave signal in the data set that you're analyzing. And so that's basically what's being shown here. So for younger systems, so the age is smaller, you get a very big exclusion region in this space. And so that's, I think, all I have time to say about this. And I'll just say that continuous waves are a complementary way of probing the existence of dark matter. You don't have to rely on binary black hole mergers to probe boson clouds or to probe different types of dark matter. You can also use them with continuous waves. And I'll just advertise a multi-messenger workshop that we're organizing in Amsterdam. And if you want to know more about continuous waves and the links to dark matter, please feel free to register. So thank you very much. I'm happy to take questions.
Thank you. Perfect timing.
Thank you.
Okay, other questions? Yeah, one over there.
Yes, thank you very much for the very nice talk. So for the primordial mass black hole, for the supersolar mass, so what kind of mechanism can circulate this binary? Because you are still far away, and maybe I'm not sure, because for normal star we have friction and Martin interaction and so on to circulate it. What is the mechanism here?
Yeah, so there are ways to do it. I don't know them off the top of my head, but certainly for the masses that are closer to like order of 0.1 solar masses, these are for sure circular. At the moment, we don't have any ways of searching for the eccentric binaries, but this is also true of the existing subsolar mass searches. So it's future work to really deal with the eccentricity that may be present.
Further questions? Yeah, I see two. Start over here.
Yeah, thank you for your talk. I think continuous waves can also be generated by pure boson star collisions. Can you comment on that? Has there been work in that?
Boson star collisions?
Yes.
But so why would it last for a long time?
Sorry, if it doesn't collapse into a black hole, you can have what's called, I think, an oscilloton sitting there and emitting waves. Okay,
so I guess so I'm not familiar with the exact mechanism of how this happens, but if the signal is slowly evolving in time, the frequency is slowly evolving in time, we can be sensitive to it. In fact, everything I say is generic towards any kind of long-lived signal. So it's just a matter of how you interpret the limits that you get in terms of a different type of dark matter star that you could have. But I'm not sure like if this is a reasonable model versus I'm not sure how to weigh this model compared to other ones.
Okay, thank you.
Yeah, there was one question over there.
Hi, yeah, thanks for the talk. Are there any standard model sources that would also give continuous gravitational wave signals? And if so, are there features of some of the models that you mentioned that would allow us to differentiate them from just ordinary astrophysics?
Yeah, so I think the ordinary astrophysics would be these like micrometer-sized mountains on neutron stars that are rotating very fast. So typically this results in a spin down, though it could be spin up. And so for the boson cloud systems, the cloud will contract as it emits gravitational waves, so this will always give you a spin up. So this is one way of distinguishing them. One other way is that if you're looking at a known pulsar, like, okay, well, in theory, you know that it's a pulsar, but perhaps it could be like like what Masha talked about today, but like a dark matter star as well. But in terms of the direct interaction of the interferometer, since the interaction is local, there's no Doppler effect. So we are sure that it's not a neutron. We are sure we can distinguish that because it basically looks like a noise line, just with some stochastic frequency fluctuation. So those are some of the ways that we can distinguish. But it's a very hard problem, especially if you have an unknown source. It could be a boson cloud, it could be a neutron star. It'd be more difficult, I think.
Okay, any other question? If this is not the case, then we break for lunch. Again, if you need inspiration for restaurants, there are many around here, but you can also look on our Indico page or just follow one of the local people here. Before I stop, I want to thank you again for this wonderful talk.
Thank you.
Yeah, thanks a lot, and maybe we all meet again in Amsterdam.
Yeah, hope so. Hope so.